Okay, so welcome to our meetup. Let's take a look at the things we're going to cover tonight. We'll start out, I just want to make a few brief comments about grading matters, and then we're going to talk probably about half the time on pulling data from the web and half the time on how to manipulate and explore that data just a little bit. So we'll look at some pretty simple examples. I know that the binning data and outlier detection stuff, that was listed in the week 5 materials, and that got shuffled around a little bit and we dropped the ball, and so we'll pick that up tonight and make sure you at least have a good idea how that works. Okay, so first on grading. Project 1 is graded, so everybody should be able to find their grades for Project 1 in Blackboard. Let me know if not. And the primary way of grading it was to run your functions against a test data set that I had created. And if you gave the correct answers, if your functions gave the correct answers, you got full credit. I did occasionally make a comment that you could improve your code or improve its user friendliness by doing certain things, but I didn't take points off if it ran correctly, right, since that was the objective. So go ahead and take a look at the feedback on that. If it didn't run correctly and I could spot the simple fixes right away, I let you know. For example, we had a few people that just had a couple simple typos, and if I could fix the first function quickly, I fixed it and then ran your later functions using it. If I couldn't, I used my entropy function with your later functions to see how those worked. So check out the feedback. If you have any questions, let me know. A lot of them looked really good. A couple of them even looked better than the solution set that we put out there. But those were pretty good. I'm about halfway through Project 2 as well, and I'm going to have those up for you by the end of day tomorrow. I haven't posted any of the grades yet because the last thing I do is generally go back and make sure I've scaled everything correctly and so on. So, but a lot of those are looking pretty good as well. So let me know if you have any questions on that. You know, the quizzes and assignments, we do have the discussion, we have the solutions posted. Discussions, you know, if you're making an honest effort and we see you in there doing good work, you get credit for those since the focus of the course is on the projects. Just as a reminder, every week from this week forward, I should have office hours on Tuesdays at 7:30. You can also set up an appointment with me outside of that time if necessary. The hour before that is office hours for my statistics class. And the link for that is, of course, in GoToMeeting, in Blackboard. Look for the Meetup office hour link. Are there any questions before we begin? Okay, interrupt if you have a question. So the first thing I'd like to take a quick look at is just how to read HTML tables using the XML package. And there are various packages for doing these things. This is the one that's covered in the book. And in particular, what we'll be interested in is the read HTML table function. And we'll take a look at this in RStudio here in just a minute. One key limitation, though, of this package, in order to read tables, they have to be well coded, and that's not always the case. It's getting better as more and more websites are created using software rather than by hand. But at the same time, some of those software packages are making them very complex, and that's interfering with the ability to read them cleanly as well. So this will let you read simple tables off the web, but it's not always a smooth and perfect process. So let's take a look at this in RStudio. The first thing I'm going to do is I'm going to pull lists of passengers from the Titanic. So here's the website that I'm going to work from, Encyclopedia Titanica. They have a number of web pages that list passengers and various details about those passengers. I'm not going to pull all of them, but it would be relatively easy to pull all of them. And we can see here the information that's given. You've got a name, age. This page is all first class. You've got their ticket number and price for a lot of the passengers. where they joined the voyage, and so on. And so let's take a look at how we would read this into R using the XML package. So first, of course, I'm going to require that we use this package, and then I often find it better, for me at least, just to create the URL as a variable here. So I've got URL for the first class passengers. You can do it all in one line, but then it's a very long line and it's not as easy to diagnose typos. So I always set it up as a URL, as a variable, and then I run the function against it. And let's just take a look at this function here. I'll make it a little bit larger for you here. So we're going to issue the read HTML table function, and we're going to call it on the URL that I created in the previous line. And I'm going to say I want the first HTML table that it comes across. If we go and we look at the source code for that page, we can figure out from the source code which HTML table we want. And you can see here, web pages are getting very complex with the code that's being used now. So you have to do a little bit of work to find. You could just do a Control F and search for the first table, and we would find it right here, the first table, and it's going to have all of that passenger information. But the table you want might not always be that first table. So we'll take a look at what you might do if it's not in just a second. We'll see an example where we want a different table. But you tell it which table by saying which equals 1, or which equals whichever number you want. This table has headers, so I'll say header equals true. And one of our favorite parameters to set, strings as factors, I'll say equals false, so that the character data comes in as character rather than factor data. And when I run this command, it takes a second to read the web page, and I know there was a comment in one of the discussion threads, I believe it was Shipra, who says sometimes it runs very slowly and it seems to hang up. And yeah, if it's a very large web page in terms of code, that's not uncommon. This one, it ran in about 2 seconds. And it pulls it in as a data frame. So here's my passengers.first data frame, and I can view that. And we see that it seems to be pulling things in correctly. I do want to make note that sometimes it'll struggle to pull in what's there. So you'll see it's got the special character with the question mark, because it doesn't know how to handle the information that's in that table. In fact, we can also see that it pulled in a blank column at the end there. You can see that thin blue line. That's where the images were for the photos of the passengers. So even though we've managed to pull this in successfully, we probably still have quite a bit of work to do to clean it up. So this is not a cure-all that works really well for every single HTML table you might want to pull in. So just be aware of that as you pull in different tables. You want to take a look at them, and you're going to have to process that data quite a bit. I'll just quickly pull in the second-class passengers as well. And one of the things we might want to do is pull all of the different tables and then merge them. So you guys should know how to do that by now. We can look and see that they do have the same columns. And we could test for that if we felt it necessary. And then, once we've done that, we can just do a row bind. And now we've got our complete passenger list, or at least complete for first and second class. And there we go. So that's the easiest way I know of to pull in an HTML table from a web page. It's a little bit clunky. It's not perfect. It doesn't always pull everything in exactly the way you might want. And if it doesn't recognize some of the characters, you might get those weird symbols, and then you got to deal with that. As a second example, let's take a look at this web page from Wikipedia, our favorite source of information. And I just want to use this to illustrate how we would pull in a different table instead of the first one. So the first table is a list of all the presidents, and we can see that as we scroll down. There's a second table, however, that has living former presidents in it. And so I'll just illustrate how to pull that table into our studio as well. And as always, I'll make this sample code available afterwards. So again, I'm going to use the XML package. I don't actually have to load it again since I already had loaded it, but it's not a bad idea to keep that in there. So I'll again specify the URL, and then I'll read in that second table. So you'll see the way I do that is by setting the parameter which equals 2. So let me run that line, and we'll see that we get those 4 presidents listed. And again, they've got some special characters in there that we would have to clean up. And that's not terribly difficult to do. It's just it takes a little bit of work on our part. Okay, a little bit more interesting example, at least from the standpoint of the complexity of the task. One of the things I've been working on recently is some hockey analytics. We've been talking to some of the different teams. Anybody who knows anything about hockey knows that Detroit, of course, is hockey town. So there's no other team worth studying, right? He says to a bunch of people who are probably Rangers fans. But the NHL has a lot of data out there on the web that you can get for free. And so here's one page, for example, that I've been trying to process cleanly. This has time on ice data for each player for each team. So this is the home team page for a particular game, and this is all data for a single game. So it's got the start and end of their shift, and it's got, if you can, let me make it a lot bigger. You'll notice here that it's got the start time both in terms of number of minutes elapsed and the number of minutes remaining in the period. So there's a lot of cleanup work on this data. And of course they've got it in both English and French, which is wonderful. It's an interesting question whether they do that for every team or just the ones from Canada. But this is not an easy page to scrape data from, and the reason for that is if I go and I look at the source code, again, a lot of these pages that are generated automatically are very complex code, and one thing that makes this page extremely difficult to pull is that I believe this is the second table tag, and you'll notice that the first table tag is only a few lines above it, and that table is not brought to an end. Oh, excuse me, there are several in here. That table is not brought to an end before we get to the next one. So they've got tables nested within other tables. And so one of the really hard things about pulling this data set is knowing which table you actually want to pull. And so if I go back into RStudio, we've been working on this code for a while. Again, I'm going to use the XML package, and here instead of using require, I don't know why I used library. And then I also, I don't believe I use it anywhere in what I've got in this code, but that string R package is a useful package for processing character data. And so I'll show you in a second the full code that I've been writing to do this. I've got a complete game list that was pulled, so I'll just read that in quickly. And then this is the code here that pulls all of the time on ice data for these games. And you can see here I make use of the read HTML table command, and I'm pulling the information for the home team and then separately for the away team. And right now I believe the table I'm going to want is the first one, but what I've got this set to do is pull all of the tables on the page. So if you look at the read HTML table code that I've got here, there's no which parameter. So I'm not telling it to pull the first table or the second table or any particular table. And if you do that, what ends up happening is that it pulls all of them. So let me run this code quickly, and I'm just going to say n equals 1 here just to pull the first game's data. But really what I ultimately want to do is pull all of the games. So I've got a list of the games and I pull all of them. But for demo purposes, we don't want to sit here for an hour while it all downloads. So I'll run this code, and now I've got this away table variable here, and it's a list of 30. There are 30 different HTML tables on this page, and I can see what's in each of them by just asking for the output. So if I say away table, and it's a list, so I'll use double brackets, and let's say what's in the 5th table? Nothing. So that's not all that helpful. What's in the 8th table? Nothing. I think the 10th table has some content. Yep, and so there's a ton of content in the 10th table. And this looked promising at first, but it turned out that was not the easiest one to work with. So the one that we end up working with in our code is the first table in in the list. And let me just show you here. So we've got away table list, which says use home table 1. So it's pulling in the first table. So if I look at home table list uses home table 1. So if I look at home table list 1, this table is the one that we've found easiest to process. Even though it doesn't look like it, if you go to the right place, eventually you get to the data that you need. Here it is for start and end of shift, and so on. So this is an HTML table off of the NHL website from their real-time scoring system that you can actually, or at least in years past, you've been able to pull it during the game. So one of the things we're working on is, how does a coach evaluate how well their players are playing during the game? So you can imagine that if we can pull this data live, from the NHL website during the game, you could actually have a printout or a dashboard or something that you could give to the coach during intermission that he could look at quickly to get a sense of how different players are doing. They already have a sense of how their different players are doing, right? Any good coach would. But sometimes this could be useful to them. In talking with the different teams, they've said there are some things they'd be interested in being able to see quickly during those intermissions. So this is a work in progress. There's a lot of work to do. If you're curious, the reason I use string R is because here's the code that I just showed you at the beginning of the script, and here's a partial script, it's not even finished yet, for processing all of that data and cleaning it up and getting it into a usable format. So there's a ton of work that goes into using these HTML tables after you pull them. So be aware of that. Pulling web data is sometimes very simple. Other times it's not nearly so simple. So let's talk about a couple of things that are a little bit easier to use if they're available. And so let me go back for just a second to the PowerPoint presentation. So that's the XML package, and you'll work with that a little bit in your quiz that's due tomorrow. You probably already have started working with it. Just so you know, there is a large set of parameters that you can set. Some of the more useful ones, we already saw that you can set the header equals true or false to say whether the table has headers. You can also set the data type for each column by providing a vector of data types for the columns if you want to be explicit in the column data type. And then you can have it trim white space. So take a look at the help file for that package, and you can read more about how to use some of these different parameters. Those are the three that I use the most: header, call classes, and trim. Okay, web services. They're a little bit more advanced and make your life a little bit easier when they exist, but that's the key. They have to exist. So typically there's an API, and the package that I'm going to show today, I'm just going to show the very basics, is the R curl package, which you can also use, by the way, to pull HTML data. But it's for this, I'm just going to show how we would use a web service. So typically the first step is to actually go and read the documentation and understand how the API works. Once you've done that, find the methods you need and the inputs you need, and then look at the results that you get and make sure you understand what's coming back to you. Let's see, so I see a question here in the discussion board. Header can also take a character vector for call names. I've never done that, so I'll be happy to take a look at that and see if we can figure that out. But I'm not sure how to do that. I read things in and then I give a name of the columns in a separate command because I don't know. It generally, the more you put in that single line, the harder it is to make sure it works right. So the documentation, you can get to it through RStudio, and you can also you can get to it at this website, and this presentation will be available to you. So an example that I pulled from a book, and I'll give you the title of the book in just a minute. Oh, here it is, XML and Web Technologies. You might be interested in studying protein sequences, and one of the problems with studying protein sequences is a lack of consistency across data sets. And so There's a website by a group, the European Bioinformatics Institute, that offers various web services that you can use to try and deal with that. And there's the link to get to their About page. They've actually changed it, but it redirects. And and here's the book on what we're going to do. But let me jump over to RStudio again and show you how this actually works. And again, if you're like me, you're often working with people who provide you the data in a nice structured format. You might not use this that often, but if you're doing a lot of work to go out and collect data on your own, getting to know the details of these different packages is really useful. So the package is rcurl, so let me load that. And the first thing I want to know is what are the databases that are available. So this is the URL from that web service that will tell me that. And there's a function in the rcurl package that says get URL content. And so when I run that, I get a list of databases that are available. And it comes in an odd object. It's not a vector like I might want. So I'll just change it to a vector here, and I'll print it out. And these are all of the databases that are now available through this web service. You can see the complete list here. And so you might be looking for one in particular, and you can see that it's in the list, and then you can use it. And then to actually pull the data that I'm interested in, I again need a URL, and then I use the get form command will actually pull the data that I'm interested on these two different databases here. And then once I've done that, I can run the XML parse command, and if I actually take a look at what that does, we'll see that it parses the data that come to me into XML format. So I can actually see it now properly set up into XML format. If you're not familiar at all with XML format, the simplest example of it is XHTML, which is what most websites are now built in. So if you go look at website source code, you're looking at XML content. But it's more general than that, right? And we'll see more examples of it, especially when we get to MongoDB and document storage. Let's see, Paul's asking what accession is. So this is an example out of a book. I don't do work on proteins. So that's a feature of proteins that they're exploring, and I have no idea what it means. So again, I have the luxury of working for companies that provide me with structured data. So my use of rcurl is a little bit limited and primitive. But I guess the good news is we're not expecting sophisticated use for this class. I'm reluctant to say that, right? But just being able to access a web service and pull the data, you're going to have a chance to play with that a little bit in the next assignment. Let's see, Shipra is saying she came across HTTR package. I haven't used it before, but if it really does pull in all of those packages, that's plenty, right? There are a lot of packages that pull in other packages, so if you load that and it loads the others, that's great. Okay, again, you'll have a chance during your assignment to play a little bit with a web service, and we can work on that during office hours or by appointment as well. If you're having trouble, we'll figure it out together. There is one other package. There are a lot of other packages, but for the assignment, you're actually going to investigate the rvest package to see how to accomplish some of these tasks. So one of the things you can do is compare the different packages, see which ones you like, which ones you don't. There are, I don't know how many packages there are for this stuff, but probably dozens out there. A few of them make it into CRAN, and so find one you like and use the one that you like. Make sure you understand how it works. Okay. Let's shift gears now. So we've talked a little bit about obtaining data from the web. One of the things from last week's list that we didn't cover, that we'll cover tonight, is how to bin data, and we'll keep it pretty simple. But we often have data that we need to bin or group or chunk, however you want to put it. You can imagine if you're running data mining algorithms, there are a lot of data mining algorithms that don't work with continuous data. So you have to bin the data into groups. So not an uncommon example would be age groups. So you might have data that, thanks Bryant. I think we looked at a jury data example a couple weeks ago where instead of giving you the actual ages, I just said something like young, middle-aged, and old, right? And you might have more groupings, but the idea is to create bins rather than to have the numeric data. Salary is another one where you might group them into, super rich, rich, middle class, lower class, and grad student, right? So, all sorts of ways where we might want to bin our data. So we're going to take a look at an example. I'll generate a random vector from the Poisson distribution, and then we'll take a look at how to use the cut function to bin that data. And the simplest parameters that are worth knowing, x is just going to be the vector itself that we're going to bin, and it can be a column in a data frame or it can be a standalone vector. Breaks is a vector that tells it what are the boundaries for the breaks. And then labels, you can give each bin a label. And so we'll look at those three things and how to do that here in just a second. So let me clean this up just a little bit. Let me get rid of that down there. And let's take a look at some code that bins a vector. So here is, I'm going to set a seed so that you guys can reproduce this later exactly as is. And here's my random vector. It's going to have 5,000 observations from the lambda equals 25 Poisson distribution. If you don't know what that is and how that works, we cover that in 606 in probability and statistics in quite some depth. But it's another probability distribution. Most of you have probably heard of the binomial distribution. It's just another one of those. And so we can just take a look quickly at what the data set is like that I just produced. So here's a quick plot of it. And so it's a discrete distribution, and it comes up with numbers. The mean is, the expected value is 25, and then it's got some variability around that. It looks like a normal bell curve, but it's not quite. The Poisson distribution has a lower limit of 0, and an upper limit is not set. So in theory, it can be as high as we would want. So this is often used to model things like how many customers will come in during a given time period, or how many traffic accidents might happen at an intersection, where we don't want to specify an upper limit, where we want to leave it as, typically we would expect 8 customers during this lunch hour, but we could have a really busy day where 200 come in, right? So we don't like to set an upper limit. So that's the Poisson distribution, and this is a graph of my sample from that. So let's take a look. We might want to not have quite so many different possible values here, right? We might want to bin these. And so what I will do is I will start by binning them into groups by intervals of 5. So one caution here, I'll show you a broken version of this first to show you what can go wrong here. Let's suppose I started my bins at 10. So I'll create break list. It's just my list of breaks at 10. And then I'm going to use the cut function to try and cut them. And then if I want to plot that, all right, here we go. But we should be careful, because if I run a summary on my vector, the minimum value is 9. And 9 is not getting included in this plot, right? You can see that in the plot, the minimum value is 10. So you want to make sure, you got to be careful that your list of breaks includes all of the values. So I've got a minimum of 9 and a maximum of 45. So knowing that, I can set up my breaks just like this. So Charlie, could you elaborate on that? What doesn't have to be discrete? Or am I missing a joke here? The Poisson distribution, it is a discrete distribution. It gives outputs of 0, 1, 2, 3, 4, and so on. So Adam, how do you decide where to break? That's a great question. For this, I'm just doing arbitrary breaks. In fact, you can see here I say this example is just arbitrary. We're going to see here in just a second a couple of other ways we can break it. Yeah, Poisson doesn't ever output 23.4. It might have an average of 23.4, but it's always a whole number that comes out of that. Okay, let's take a look at another way to bin these that's still arbitrary, but now instead of having these intervals down here in my plot, I'm actually going to assign group names, and I use the labels parameter to do that. So you can see down here that each interval is it's an open interval on the left, so it means greater than 10 and less than equal to 15, for example, for this first bin. But I might not want that to be the name of the bin. So what I'm going to do in the second example here, I'm going to just create a list of labels, and I happen to know that I have 9 bins, because remember that 5 to 10 bin is not showing up on that plot yet. Actually, here I'll just, oops, there we go. Instead of having the intervals show up, I'm going to give them labels, and I'm going to use the letters A through I. And just as an example, I could have, if I know I want to use letters, you can also use the letters vector to determine how many you need. But there are, there we go. So let me run again the grouping. And now when I plot them, you'll notice that instead of the bins, it gives the letter name for each one. So that's a useful thing to do often if you group them. So if you're grouping ages into different groups, you can actually name them as you see fit. So young people, old people, and so on. Okay, so Adam asked, how do you determine where you want to group them? It just depends on context. But for instance, one thing that's not uncommon is to group them by quartile. And we're going to need to know how to do quartiles in just a bit anyway. So just as a quick note, I run the summary function on my vector, and it gives me my quartiles, right? It says the 5-number summary, the minimum is 9, the first quartile is at 22, the median's at 25, the third quartile is at 28, and the maximum is at 45. So that's my, my breakdown for quartiles. There's also the quantile function, and what that does is it gives you the cutoff for a particular percentile. But it also, if you don't tell it what percentile you're interested in, if you just run the quantile function on a vector, it gives you those same quartiles. So the summary function gave us the mean as well, right? If we look down here, it gave us the mean. But when we're working with quartiles, we don't care about the mean. So if I do quantiles instead, by just running the quantile function on my vector, what we'll see comes out of that is those same quartiles, right? 9, 22, 25, 28, 45, but I don't have the mean in there, and now I can refer to them by their position in the vector. And this is a named vector, so it puts the name of each of those cutoffs in there, and then it puts the values. So if I want to group my observations by quartile, I can create that list of their quartiles, and then I can use that as my breaks. So let me do that here. I'll group by those, and again, I'm assigning them labels by which quarter of the data they're in. And then let's take a look at a bar plot. And let's see, it looks like you guys are discussing those intro stats classes where you would have learned all that. Here's a question for you. I just broke the data into 4 quartiles, and in theory, these 4 bars should be the same height. Why aren't they? Anybody know? We haven't done anything wrong. Anybody want to venture a guess why they're not all the same height? That's a good try, Charlie. Not quite. you're on the right track. All right, so the answer is that there are ties. And so when we calculate the quartiles, some of the 22s end up in the first quarter of the data, and some of the 22s end up in the next quarter. But when we do the plot and when we assign them to their groups, they all end up in the same bin. So all these 22s that got split between the first and second quarters are piled into that first bin, and so they're not the same height. And so there are probably a lot of ties around the break between Q2 and Q3, right at 25, and then there are probably a lot of 28s as well. So the same thing is happening there. So that's why it's not going to be exactly all the same height. How do we decide how many bins? Again, context matters. If you're trying to build a predictive model, you might want just 2 bins. You might want 3 bins. It just depends on context. And we're going to do a lot of that when we get to the data mining course. We're going to find a lot of the methods, including the entropy method that you guys all programmed, require us to bin that data and have categorical variables. Okay, let's move on. So that's how to bin data at its simplest, and you guys can play with that and explore that and see what you can make of it. Let's talk about outliers just briefly as well. And again, I'm going to limit this to what you would typically cover. Well, I'll just say what you would cover if you took my intro stats class. Not every teacher goes into the same level of detail on this, but we're going to look at 2 different approaches. Let me actually go back to my slides for a second. The 2 different approaches that you should have heard of. One is using standard deviations and those things called z-scores, and the other one is going to be to use the quartiles and the idea of box and whisker plots. And so we'll take a look at both of these here. For the z-score approach, 4 steps. First, you got to calculate your mean, and then you calculate your standard deviation. Then you determine the interval. That's 3 standard deviations in each direction. Some teachers will say 2 standard deviations in each direction. That's a judgment call. You have to decide how far out you want things to be before you consider them outliers. But typically 3 standard deviations is the rule that I use the most. If you want more outliers, for instance, if you're doing some sort of a fraud detection project, you might want to identify the best candidates to investigate. You might lower that threshold and say anything outside of 2 standard deviations so that you have a larger list to investigate. And then you might start investigating the things that are the furthest out first. There's no hard and fast reason for using 3 standard deviations. It's just the most common. 2 is probably the next most common. And then once you've identified how far in each direction you're allowed to go, you just have to identify all the observations that are further out. So we'll take a look at that here in just a minute. And then the other approach, what I typically call the P approach, is based on percentiles or quartiles. This is where you do the 5-number summary with those 5 numbers that we did before. Calculate the interquartile range, which is just Q3 minus Q1. So how spread out is the middle half of the data. And then determine the interval that starts at Q1 and goes 1.5 of those interquartile ranges below, and then start at Q3 and go 1.5 interquartile ranges above. And so that gives you what we would consider typical, and that's how far out the whiskers typically are allowed to go in your box and whisker plot. And then again, just like before, we would identify anything outside that range. This is not quite the same as Windsorization. When we do Windsorized means, we still use the z-score approach, but we chop off the observations at each end to calculate a Windsorized mean. It's an attempt to make the z approach a little more robust. And that's actually why, let me back up a slide, this z approach is probably the most commonly used, but it's highly dangerous to use it. And the reason is, if you have outliers, that affects your mean and your standard deviation quite a lot. And so if you get rid of even just 1 outlier, you can often have a drastic reduction in your standard deviation. And now, so what now do we do? Do we recalculate the standard deviation and then check again for outliers? So it's not what we would call a robust technique. So it's the most commonly taught in intro stats, and that's a mistake, I think. I'm highly opinionated about intro stats. You'll discover as we go. The P approach is a little bit more robust because it doesn't rely on those extreme observations, right? It just looks at the middle half of the data. And so if you have one or two extreme observations, they'll still get flagged, but that won't affect the whiskers. It won't affect what's the typical range. So let's take a look at these in R. Again, if you're not following the statistical details too closely, we are going to spend a lot of time on that when we get to future classes, both the statistics class and then also the data mining class. And we're going to learn some other outlier identification techniques as well that are a little bit more advanced. Yeah, with a single tail, you can still use them, Charlie, but neither one of these methods is the most reliable anyway, so I would use the P approach if you're going to do that, though. And so you still can use it, but again, these are the simplest methods, which is why they're taught in stats, but they're not the best. So let's take a look at how to work with these. So we'll start with the Z approach. And I'll show you how to code it by hand. And that might help if you weren't following along with the math there. So step one here, I'm going to calculate my mean. I'll call it mu. Calculate the mean of the vector. This is a good time to remind you that the mean function doesn't like to work with missing values. So I'm going to remove any. There aren't any in this vector, but just as a reminder, that's not a bad idea. So my mean, you can see it over here, is 25.0236. That's good news. If my Poisson distribution had a parameter of 25, that's what we expect the mean to be. So we're pretty close on that. The standard deviation we are expecting to be about 5. It's the square root of the parameter. And so when I calculate that, you'll see I get 4.96. So that's pretty close to 5. And then what I'll do is I'll say 3 times 4.96 in each direction from the mean. So my lower limit is going to be the mean minus 3 times the standard deviation. And then the upper limit is going to be the mean plus 3 times the standard deviation. And we can see the lower limit then is going to be 10.13. The upper limit is going to be 39.91. Anything outside of that range we would then consider an outlier. So if we have a 10 or a 9 or an 8, that's going to be an outlier. If we have a 40 or a 45, that's going to be an outlier. And what I'll do now is I'll just say, give me a list of the outliers. I'll call it out.z since we're using the z approach here. Take my vector, but only take the entries that are less than lower or greater than upper, that are outside of that interval. And what we'll see there is I get a vector that has, quick math isn't my strength, we have 15 outliers. And if we look at what they are here, I had it print them out. Most of them are 40, 41, a couple 43, 45, and then we got a 9 on the lower end, a 10 on the lower end. So we're getting a list of all the ones that are outside of that range. If we were more interested in the position of them, we could get a vector that has the positions of them. Just using a Boolean vector. But now I can play with this. Once I set up the interval, I can just say what's outside that interval. There's a shortcut here. There's a function called scale that by default it will standardize the vector. Let me run that quickly. And what you'll see here is that the scale function, if I don't pass it any parameters, it's for all 5,000 observations, it's calculating the z-score, which is to say how many standard deviations is the observation away from the mean. And you can see most of them are in the 0 point or 1 point range. Right? Here's one that's 2.4 standard deviations away. So what we can do here is we can use this to say, give me all of the observations where the absolute value of the scaled value is greater than 3. And so that means their z-score is greater than 3, which is that they're 3 standard deviations or more away from the mean. So that's a shortcut, but again, in this class especially, I'm not interested in clever code. If you wrote the code that I've highlighted, that works just fine, and I'm not going to penalize you for using that instead of the scale function. It's much more important that your code runs well and that you can read it and understand it clearly rather than be clever. I'm not going to punish clever either, but don't worry if you don't use the most clever techniques. Okay, let's take a look at the P method. So this is using the quartiles. So I could use what I did above where I just get a list of the different quartiles, but I wanted to show you how you can get a specific percentile as well. So what I'll do is I'll create this QT3 for quartile 3, and I'll use the quantile function, but I'll say I want the 75th percentile. So in R, the quantile function is essentially, it's just a percentile function, but they call it quantile probably because the default, if you don't provide a percentile, is to do the 5-number summary. But if I want the 75th percentile, I can use the quantile function and pass it my vector and 0.75. And when I do that, you'll see over here QT3 is 28. And then I'll do the same thing for the 25th percentile, which is Q1. So QT1 gives me a value of 22. And now I'll say my interquartile range is just QT3 minus QT1. And so the interquartile range comes in at 6, right? 28 minus 22 is 6. My lower fence is then start at my lower quartile and go 1.5 interquartile ranges below that. And the upper fence is 1.5 interquartile ranges above the 3rd quartile. And so my lower fence is at 13 and my upper fence is at 37. So by the P method, anything outside of the interval from 13 to 37 would be considered an outlier. And again, I can run that same line and use these values. And my outliers from the P approach, I've got a lot more of them. I've got 67 of them here. So I'll print those out quickly. And there's a list of all of the outliers by this method. Typically, the P method is a little bit more conservative. It's more likely to flag something as an outlier. Right? The Z method, especially when you have really large outliers, you might miss some that you might have otherwise flagged. So the P method is a little bit more robust and a little bit more conservative, so it tends to be my method that I go to first. Sometimes I'll use both, sometimes I'll just use Z, but most of the time I'll use this P method. Quartiles are just more robust. What to do with these outliers? Well, that just depends on the context. If you're building a model, Jordan's got it, right? Just toss it if you don't like what it does to your model. Often we're actually looking for outliers. They're the interesting things, and so rather than throwing them out, we might actually just flag them as outliers and then go and investigate. At the very least, we might investigate why they're there. Could it have been a data entry error? Right? If you're looking at ages and you get an outlier where somebody is 350 years old, my guess is that that was 35 years old or something like that, where there was just a typo. So what you do with outliers just depends on what you're trying to accomplish. Let's look at how to do this in a visual way, the P method. And that's just a box plot. So I'll create a box plot of my vector. And there it is. You can see the median is the line in the center of the box. And Q1 is the bottom of the box. Q3 is at the top of the box. And then the whiskers go out 1.5 times the height of the box. So you can actually visualize that, right? The height of the box there, if that were 1 inch, this top whisker would be 1.5 inches above the top of the box at most. So what happens is you stretch the whisker out to that range, and then you let it collapse back into the next observation. So if there wasn't an observation out at 37, I believe it was, right? If there wasn't a 37 in the data set, if there was a 32, the whisker would then be collapsed back down to 32. So you go out 1.5 times the interquartile range, and then you collapse to the next observation in. So that's why you'll often see a box plot where the whiskers aren't the same length, because they've been collapsed in. But in this case, we actually do have observations at 37, so it doesn't collapse in. And the same thing on the other end, right? It goes all the way down to 13, and there is a 13 in the data, so it stays there. And then the circles outside of those whiskers are the outliers. And there are only, let's see, it looks like 11 circles, and that's because you've got several outliers with the same value, so they're just overlapping. You can do, I'm going to look up the syntax. If you prefer to see a box plot horizontally, horizontal. Okay, so what we'll do is just do the same command, but we'll say horizontal equals true, and you can get a horizontal box plot if you prefer that. It's just up to what you want. And Brett is pointing out that there's a way to get the actual values, right? So maybe jot that down too if you're interested in that. We're almost out of time. I just want to show one more thing with percentiles. So using the quantile function, you can actually find out what's the cutoff for a particular percentile. You do sometimes want to go in the other direction. So you might say, I want to know what percentile a 32 is. You know, think about when you took your standardized tests back in the day, where you were told you were in the 98th percentile or the 45th percentile or whatever percentile you were in. So they took your score and calculated the percentile. And so here's a clever way to do that, a quick and easy way to do it. I'm going to say percentile.32. I want to know what's the percentile, or how many observations, what percent of observations are below 32. And so what I'm going to do is I'm going to take this logical vector created by the command vec less than 32. If I run that, you see I get true and false. So if the observation is less than 32, it would say true. If it's greater than or equal to, it'll say false. And I want to know what percentage of the observations are less than that. So when you take the mean of a Boolean vector, right, it uses a 1 for true and a 0 for false. And so if I take the mean of this vector that's 5,000 long, what I get is that 90.28% of the observations are less than 32. So 32 would be the 90th percentile, roughly. So that's a way to identify what percentile a particular observation is. Whereas the quantile function goes the other direction. It tells you what number would be the 75th percentile. This gives you the number and calculates the percentile. Okay, the other thing that was mentioned in the material for the week was correlation analysis, and I am, particularly since we're out of time, I'm going to pass on that for this week and say you're going to study correlation analysis in much greater depth in IS 606 when we get to the statistics course. But just so you know, if you want to investigate correlation, the core function, COR, calculates the actual correlation coefficient, and then you can test whether it's statistically significant using the core test function. And if you're interested in those, let me know and we can talk about them one-on-one. If it's relevant down the road in the course, we might come up with it again. Otherwise, look forward to a lot of that in your stats class. So we got about 2 minutes left. I'll just ask if there are any questions at this point. Okay, let's stop there. Again, Project 1 grades are in. Go take a look at that. Let me know if you have any questions. Project 2 grades, I'm about halfway through them. I'm expecting to have those up by the end of day tomorrow. And then I'll start picking back up with the quizzes and assignments that need to still be graded. Let me know if you have any questions or concerns, and we'll go from there. And I'll see you all in 2 weeks, if not sooner.
Thanks, Mike.